All right. You get to relive some of our fond memories of the chain rule. Because like I said, once we started into integrals, just like with derivatives, there's so many different techniques to derivatives that you have to deal with. But for every one of those techniques, we had to be able to undo every one of those techniques. So we had to have ways of being to undo what you did. And that's what we will just start out with respect to one technique. And the idea of if I have a function x squared plus 5 to the 9th power, and I want to take the derivative of that, what is the derivative of it? This is good review for us to go back over this technique because next week you'll be doing it again with respect to your final. The hint is try your chain rule. And once again, I know we're reliving fond memories from December. We are taking our exponent out front. X squared plus 5 inside. Drop our exponent by 1 to give us 8. But then we have to multiply by what? 2x. We have to go inside, take our derivative. So we have 2x and 9. We can combine to 18x. And then we have x squared plus, x squared plus 5 to the 8th power. So that was our derivative utilizing a chain rule. Well, as I referred to, everything in mathematics we need to be able to undo. Well, we have to be able to undo that derivative to go back to where we originally were. So what we would have to do to undo the derivative is we can take the antiderivative of 18x times x squared plus 5 to the 8th power dx. Well, the only technique we have right now is the antiderivative of ax to the nth dx is a divided by n plus 1 times x to the n plus 1 plus c. That is the only technique we have. Our exponent rule we have with respect to antiderivatives or integrals, we can deal with that. Well, this is not in that form. This here, if I wanted to, I could take x squared plus 5 times 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 x squared plus 5. I could, if I want to, multiply all that out. Yeah, that's exactly right. Is it doable? Yeah. Would it be a try in our patience? Yes, it would be. Would it be filled with mistakes? Probably so. So to multiply that out, to get it into the form of ax to the nth would be a lot of work. Plus, after that, distributing through 18x, the multiplication of that. So, how do we find a technique that allows us to be able to solve this antiderivative where I don't have to multiply out 8 terms of x squared plus 5? Well, the technique we're going to use is called integration by substitution. This integration by substitution will undo our chain rule. This will undo the chain rule. Well, what we need to do is we need to work with the idea of substitution. So we're going to let t equal something. So if I look within the problem, a nice little way of trying to figure out what we want to let t equal is a value that is quantified to a power, or maybe a denominator, maybe stuff that's inside a square root, because if it's inside the square root, that's being quantified. So you look for that to let t equal that value, whatever that value is, the stuff that's inside, not to the exponent and not with the exponent, just the stuff inside that quantity. Well, the stuff that's inside the quantity is x squared plus 5. This is the value that's inside the quantity with an exponent of 8. The next step, once we figure out what we let t equal, we take the derivative. We take the derivative of t with respect to x. Once again, with respect to x, the dx on the bottom just tells us that's what we're going to utilize the exponent rule to. And once again, we have to go back to the idea, this is derivative. We're taking the derivative of t. So this is where students tend to start running into problems, because we're talking about integration, but to do the integration, we have to do a derivative. So I need to make sure in my brain that I'm doing the right rule here. So I'm going to take the derivative of x squared plus 5, which is what? 2x. Again, my exponent goes out front, drop my exponent by 1. And what we want to do is now solve for dx. Well, to solve for dx, I can multiply both sides by dx. So we have dt is equal to 2x dx. And then we can divide by the 2x. So dx is equal to dt divided by 2x. And once you do a few of these, what you'll see is whatever the derivative is going to go to the bottom, and the dx is going to come up here. And that will always be the case. Well, this technique is called integration by substitution. So what we're going to do now is we're going to deal with substitution. We are going to substitute in. So we have the integral. We did nothing with this 18x, so we're going to leave that alone for right now. But this x squared plus 5, we said is equal to the t. So we have, parentheses in there. We have t to the 8th power. We're just taking the x squared plus 5 out, which we said is equal to t. And once again, as we talked about substitution, you're replacing something with its equal times, well, the next thing I come up with is dx. Well, dx we said is equal to dt divided by 2x. So we've done a bunch of substitutions here. Now if we look to simplify, we have 18x divided by 2x, which gives us what? 9. So we're still left with the integral of 9 t to the 8th dt. Can I now take the antiderivative of 9 t to the 8th? Yeah, I can. Add 1 to my exponent. Divide my exponent by my coefficient by my new exponent. So we have 9 divided by 9, t to the 9th plus c. 9 divided by 9 is a value of 1. And then we want to back substitute. This t is equal to x squared plus 5. So we're left with x squared plus 5 to the 9th power plus the value of c. Now if I would take the derivative of this, I would come back to 18x times x squared plus 5 to the 8th. Take the derivative of my constant, that goes down to a 0. So that c could be a value of 0 also. Allows us to go back to where we started. Integration by substitution undoes your product rule. Not product rule. Undoes your chain rule. Now there's techniques to undo your product rule, quotient rules, product rule. You have something called integration by parts. You don't deal with that until Calc 2. Partial differential or partial fractions deals with your fractional part idea. Okay, so there's other techniques. There's a lot of techniques in integration. So if we take a look now at antiderivative of sine of the fourth of x, cosine of x dx. Once again, look to see what things are what's being quantified here, or what has an exponent to it. That's what you let your t equal. So what can we let t equal? Sine of x. We take our derivative, dt dx. Derivative of sine is cosine. And mentally, we're going to multiply by dx and then divide by cosine. And once again, what will happen nicely is this will always just switch. Your dx will come up here, multiplying both sides by dx, and then we have to divide by cosine. So we have dt over cosine. So now we make our substitutions. Antiderivative, we let t equal sine of x. So we have t to the fourth, then we have cosine of x times dx. dx is equal to dt divided by cosine. What happens to the cosines? These will cancel. So we're left with the antiderivative of t to the fourth dt. So I can take my antiderivative of t to the fourth and add your 1 to the exponent, divide that to the coefficient. Coefficient's the value of 1. And then back substitute. we should have 1/5 to the 5th plus c, and then back substitute. T is equal to sine of x. So we have 1/5 sine of the x, 1/5 sine of the 5th x plus c. Now the process, once again, you let something equal to t, then you take the derivative of whatever you let t equal. When you take the derivative of a polynomial expression, an algebraic expression, what happens to the exponents to the variables when you take derivatives? Yeah, you subtract one, so they get smaller. Okay, they get smaller. And this process of dealing with integration by substitution, you let something equal t, then you always take the derivative. So if I have exponents within my t, then they're going to get smaller. Well, if I take a look at my antiderivative here, I have 2t minus 5. I have t squared minus 5t plus 2. I use the variable t. So what I'm going to do is I'm going to switch this to an x, because I already have t in there. Which one do you think we should let x equal? Do we let it equal the top or the bottom here? Bottom. So we have t squared minus 5t plus 2. So we take our derivative of x with respect to t, so we should get 2t minus 5. Then dt, we can switch these two once again. We equal dx divided by 2t minus 5. Make your substitutions. What happens nicely is the 2t minus 5s cancel off for us. So we're left with the antiderivative of 1 over x dx. Now we have to remember how to take the antiderivative of 1 over x. What do we get? Logarithm. ln the absolute value of x plus c. So we have ln, back substituting in, t squared minus 5t plus 2 plus c. I'm going to switch my variable to u now. I'll take the thing that's being quantified. What's being quantified? All right, x squared minus 3. Good. Let u equal that. So du dx, what's the derivative of u with respect to x? Should be 2x switch your dx and 2x. So dx is equal to du divided by 2x. Make your substitutions. Right, square root is u to the 1/2. We have du over 2x. Simplify the 2x and the 12x. Leaving us with just 6. So we have the antiderivative of 6u to the 1/2 du. Add 1, so we have u to the 3/2. Take our 6 divided by the 3/2. Flip and multiply, so we have a value of 4. Let's see. U to the 1/2 of 3/2 gives us u to the 1/2 plus or 1.5, which is u square root of u. And make your back substitutions. If let u equal cosine of x, then du dx would equal negative sine of x, so dx would equal du over negative sine x. Problem is, this would give me u squared times du divided by negative sine of x. And that gives us a problem because we would not be able to cancel anything that we need to. So there's other techniques that we have to deal with. We can still deal with substitutions. What we have to go back to is relive our fun trigonometric days. The cosine of 2x is equal to 1, how about it? One of the formulas for the cosine of 2x is equal to 2 cosine squared x minus 1. Adding 1 to both sides, we have 2 cosine squared of x is equal to cosine of 2x plus 1. Dividing everything by 2 or multiplying by 1/2 will but we're left with the cosine squared is equal to 1/2 cosine 2x plus 1/2. So we can then, if we need to, rewrite this as 1/2 cosine of 2x plus 1/2 dx. Which once again tends to be confusing because we're going to have to deal with substitution here. This we don't have to. So we can also rewrite this as the antiderivative 1/2 cosine of 2x dx plus the antiderivative 1/2 dx. In my substitutions, I can let u equals 2x. Dx is equal to 2u or du over 2x. And this will allow us to be able to integrate. When you deal with the cosine squared of x, it gets messy. And that's sort of where we're at here. We're left with 1/4 the antiderivative of cosine of u du, taking the 2 out with this 2, plus the antiderivative 1/2 dx. If du over 2, and I can combine the 2's on the bottom out here to give me 1/4. Once again, I'm not going to give you a problem like this, but this is just it. The more that you can get involved with the problems. And doing one last back substitution, we have 1/4 sine of 2x plus 1/2 x plus c. Once again, that gets really involved. I'm not going to go to this level. If I can get you to get some substitutions in there, I'll be happy. If I take a look at my quantity, that's let u equal x minus 1. Which means if I take my derivative, I get 1. So dx is equal to du. So looking at my antiderivative here, I have x plus 1 times u to the 1/2. And my dx is equal to du. The problem we have once again is we don't have a substitute, or we don't have something to cancel out this x plus 1. But if we take a look at what happens here, we still need to get rid of this x somehow. For us to be able to integrate and then put it in terms of u. On all these other problems, except for the last one, we were able to cancel out stuff. The 2x and the 12x, we were able to cancel that out. On the front side, we were able to cancel out the 2x and the 18x. We're able to always cancel stuff out. This one we can't. If u is equal to x minus 1, what does x equal?
U plus 1.
U plus 1. Which allows us now to make one additional substitution in here. So we have the antiderivative of u plus 1 plus the 1 that's already there times u to the 1/2 du. So we have u plus 2 inside. We can distribute over both the terms. So we have u to the 1/2 times u to the first. If I have a like basis, we need to add our exponents. So we have u to the 3/2 plus 2u to the 1/2 du. Add 1, add 1. So we have 1 over 5/2 u to the 5/2 power plus 2 divided by 3/2 u to the 3/2 power plus c. This tells us just to reciprocate, so we have 2/5. We have u to the 2.5 power plus 2 divided by 3/2, so we have to multiply by 2/3, so we have 4/3. U to the 1.5 power plus c. So we have u squared, square root of u, 4/3 u, square root of u. And we can make our one last substitution for back in for u. U was equal to x minus 1. We have x minus 1 quantity squared, square root of x minus 1 plus 4/3 x minus 1, square root of x minus 1 plus c. If we take a look at problem 2 real quick. Problem number 2, we have limits of integration from 1 to 5. When you have limits of integration, there's 2 techniques you can follow. Okay, we have once again, if we let u equal this x squared minus 3. Du over dx equals 2x. Dx is equal to du divided by 2x. This dx tells us our x intervals from 1 to 5. If we do our substitutions, we have our 12x squared times u times du over 2x. So we come down to, oh, this should be a square, my bad. I goofed that up. So we have 3x squared and 3x squared. Sorry about that. So if we simplify, we'd come down to a value of 4u du. But what we have switched our variable to is we've switched our variable to u. If x is an interval from 1 to 5, what would u be the interval of? Well, how do we calculate u? U is equal to x cubed minus 3. So if x is a value 1, what's our u value? Well, u would be 1 cubed minus 3 to give us negative 2. If x is a value of 5, we would have 5 cubed minus 3, which would give us 125, 122. So I can go from negative 2 to 122 and integrate like I normally would. And make my substitutions there. We'll work on this more tomorrow. Try to get a couple days of practice with integration by substitution. This is called change of limits, which is a technique of dealing with integrals by substitution. Adios, have a good day.